Hey guys, welcome back. So in this video, we are doing the diffraction topic of wave optics. So let's start it. So what is diffraction actually? Okay. Remember before diffraction, I start look here in previous topic, ray optics. We have learned like two type of lenses. So one lens is called this type of lens is called convex lens, and this type of lens is called what concave lens, right? So if you remember that, what you have done here, suppose ray is coming here, then this lens what it do? This lens do what conversion of light, right? Now it will convert the light will meet at some point, right, after passing through this lens, right? Similarly, what this lens do, this will diverge the light, right, like that way. Yes, so these two type lenses what they're doing, they it would either they are converging the light or they diverging the light, right? Yes, exactly similar idea is what here is called diffraction of light. So what is diffraction meaning? Diffraction means what, the bending of light or turning of light around what, either some you have some obstacles, okay, or you have what, some opening which are called like aperture. So let me write few words here first so that I understand better. So how you define, so let me write few words here so you understand better. Okay, so look at this definition of what your diffraction. What definition? The bending of light rays from sharp edges of an opaque obstacle. The obstacle should be what, opaque in nature, not transparent. Like your lenses are transparent, right now. So not these. Light should not pass through that object. It should be opaque, right now. Yes. Or an aperture means some opening. What's the meaning of aperture? Some opening like in a wall or some type of hole where light is passing through that, right? Yes. And is spreading in the geometrical shadow of the region is defined as what? Diffraction. Simple meaning I'm saying that you can say like bending or you can say turning, right now, of light around what, edges of your like obstacles, right? And what type of obstacles we need? All opaque means light cannot pass through them, okay? About some obstacles, or what you say some openings which are called what, aperture, right? This is called what, diffraction of light, correct? So let's see with the help of picture how you understand. Suppose you have some object, like I say this is some object. I have placed this some object, and this is what, opaque means light cannot pass through this. It's not a transparent. If some light is coming like this one, this light coming, the light that's away, it will pass straight. The light which is coming here, like that way, these lights. So listen, what will happen when light comes here? This light will bend. It may bend like away, means it can spread or it can converge. Also, both things can happen, right? Yes. So if light is passing through an obstacle like this type, then what will happen? Light will always what? Converge, right? Light will always converge. Or aperture is there, that will diverge. So light here how it looks, these rays will meet like that way. They will converge like that way. One ray little away is passed straight. So this light will not pass through this. Isn't because an opaque object. So this is called like an obstacle. You're trying to stop the light, then the light at the edge, these are the edge, these two lights, see na, this one and this one only, these are bending around the corners, right now, around the sharp edges. These light will not pass, right? These are stopped by this obstacle. These light which are away, they will passing straight, no problem. So the light at the edges only what, turning, correct? So this is called what, a diffraction of light. This is like an obstacle. Suppose you have wall, let's say this is a wall and you're making a hole here in this wall. So this hole will be called now an aperture. This is a wall. So suppose light come like this one, light will start by that wall, then light will pass through this, right now. This is a light, then this light will what, spread after passing through this opening like this way. So this is called what, an aperture. Let me change color so you see better. So this is called an aperture, correct na? And this is what, an obstacle. Obstacle should be always opaque in nature, because if transparent is there, then this will happen like lenses and these things, okay? Okay, so this light is about bending away, right? Like this is called spreading light, right? If you have aperture, then light will spreading will happen. If this type of like obstacle is there, then light will what, converts, right now. Yes, so these are phenomena just similar to what like lenses we have learned, but lenses are transparent object, right now. Here mean what, opaque, either an opaque object place in the path of your light, or you have a wall and there is small opening which is called aperture, and light is passing through aperture, and light will what, spread, right now, and here light will what, converge. Hope you understood this. Okay, now we want to understand that when the diffraction will happen, what's the condition for diffraction. Diffraction is not happening always, we need some condition. Okay, so what's the condition, let's learn about that. Okay, so condition for diffraction is what? Okay, before this, you should understand that this diffraction happens in both type of ways. Means you have mechanical waves or EMWs. So let me write here. Diffraction happens in both your mechanical wave, like sound wave is mechanical wave, and what? All EMWs, all electromagnetic waves also, right now? Yes. So in mechanical wave, like sound wave, it can happen, and all EMW like light, X-rays, gamma rays, all UV, it can happen. So what's the condition of diffraction? The diffraction depends on what? Two things. Diffraction depends on what? Two factors. Two factor. And what these are? One is what? What is wavelength? Like you're talking diffraction light, then what is wavelength of light? You're talking sound, then what is wavelength of sound? And second depends upon your size of your obstacle or aperture. Obstacle or aperture. So it depends on what? These two things only, right? What's the wavelength of that waves you are talking, which you want to diffract, and your size of the obstacle or your aperture. So what happens actually? So diffraction will be visible actually if, right now, if what happens, your size of the aperture or obstacle, right now, is nearly equal to what? Wavelength. If these two are nearly equal, right now, then diffraction will happen. So suppose size of aperture I call A, then A should be nearly equal to wavelength, or you say like A by lambda ratio should be nearly equal to what? 1. Then diffraction will happen. So diffraction happens only when the size of the obstacle or your aperture, means your opening, is nearly equal to what? The wavelength of that wave. So if you talk like, suppose you want to get diffraction of light, right now, light, normal light, light wavelength is what? Very small, around 10 power minus 7 meter, right? This is the wavelength. So if you want to get diffraction case of light, means then the size of the object should be very, very small, like 10 power minus 7 meter. So we need very, very small or tiny object or very, very small opening to get diffraction of light. But you see, suppose you want to get diffraction case of sound, sound, then sound wavelength is what? It start from like few you say millimeter to what? Few meter, right now? Yes, few meter, like 10 meter, 15 meter, it could be, right? So you see the wavelength of sound is much bigger than what? Light. So diffraction happens very easy in what? Case of sound. So I'm writing few points here. Diffraction, let me change color so you see better. Listen carefully. Diffraction in sound is sound waves is much easier, right now? Much easier than what? Light wave, right now? Yes. Why? Because the wavelength of the sound is much bigger than what? Wavelength of the light. Light has 10 power minus 7, while sound has around like few centimeter or millimeter, we say, to what? Few meter, like up to what? 16 meter, we say. Correct. So even the big object like big buildings or doors or windows, our home, they also can diffract sound, but they cannot diffract what? Light. If big objects are there, like we have window, if light is coming, then light will not get diffracted. Here we light will behave like rectilinear motion only, like ray optics only, right now. Wave optics you cannot apply. But sound, if this is a window here, okay, normal window like height of like 1 meter or width of 1 meter, right now. Here sound easily can get diffracted, right? Yes, sound can diffracted, but light cannot be diffracted. So remember that 2 point you have to remember. Diffraction can happen in both type of waves. You have mechanical wave or you have what? Electromagnetic waves. Yes, it can happen in both. And then diffraction happens only when, like when size of the object is nearly equal to what? Wavelength, or ratio of the size of the object, or you say aperture, is nearly equal to what? 1. They are equal in size. So if you want to get diffraction in light, then you need what? Very, very small object, because wavelength of light is what? 10 power minus 7 meter. So it's very hard to get diffraction in what? Light. Okay, big objects cannot do diffractions. We need very, very small object of this size. But diffraction sound is much easier, because wavelength of sound is what? Much, much more than what? Your light wave. So diffraction sound happens much easier than what? Light wave. Correct? Okay. So now we'll talk that we'll talk about an experiment. It's called Fraunhofer diffraction, or it's called single slit experiment. Okay. 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 So we're learning diffraction due to a single slit. also called Fraunhofer diffraction. This is also for double slit, but that's not in our syllabus. We have just single slit in our syllabus. Okay, so we're learning diffraction due to a single slit. So this, what happens in this case? Uh, your source of your radiations or waves and screen. Okay, these both are placed at like effectively infinite distance away from your diffracting object. Okay, so let's write few words here. Here, what happens this type of diffraction? Your source and screen are effectively placed at infinite distance away from what your diffracting source. Okay, diffracting device or whatever. Correct. So let's understand this with the help of pictures. Suppose you have source. This is your source of light. Is producing some waves. This is source. Now we need, because if you remember starting of this chapter we have learned we need what wave fronts right now. So we need a plane wave front. How to produce a plane wave front? You can put a convex lens here in front of this, and this source is placed at focal length of this. So radiations comes here. When radiations incident on this, they become parallel right now, because source is placed at what, at focus. This like distance is simply like focal length of this lens. So source is placed at focus of this lens. You call lens L1 some name. Okay, so after the radiation incident on this, okay, what happens? They becomes parallel, right? So now we have a say we need a slit or an opening or an obstacle. So suppose here if we put a wall, this is a wall. Okay, this is some wall. So in this wall we have an opening, correct? So let me represent opening by this color, different color, so you understand better. This is a small opening, right? Yes. So here suppose a plane wave front is coming. Here we having a plane wave front because the radiations are coming parallel, so they produce what, a plane wave front. So suppose this is a plane wave front, right? This is called a plane wave front. So let's give some name A and B. This is a wave front, and it should be equal to the obviously it will be equal to size of this your opening itself. So you call this A. So A is called what, size of your obstacle, or you say what, okay, you can call obstacle also, or you can call what, your aperture also, right now, size of it, or simply call what other, you can call it what, slit width. Simple meaning will be what is slit width. So AB is a plane wave front coming incident on this wall where the small opening is there. So after passing through this, radius like light comes, suppose it's come like that way straight. Okay, now we put another lens here so that we can converse light nearby only. This is another lens, and this is what your screen. So here we want to see the what type of patterns are formed here. Okay, so this is your screen, and this is what your lens too. So the distance between your this what, your obstacle and the screen, that's we call what, screen distance D. Correct? So two things we have here. One, A is the size of this obstacle or size of your aperture or opening, and D is the distance of the screen. So what happens now? Light will come here instead of this lens. This lens will convert them. Suppose this is normal. Okay, this is at the center. So this is let's call center O. So at the center, we what happen again? Central maxima will be formed always. The bright fringe is formed. Central maxima. Like if you remember your Young's double slit experiment, there also had central fringes always white or bright, or you call maxima is formed, right? Exactly same thing here also happen here. Your central fringe will be always what, bright. Then what happen alternatively? Dark, bright fringes will be formed. So you take a general point. Suppose at this point, which what fringes formed you want to know. Okay, some P point. Then what you do? Let's say radiations coming like that, and they meet what at that point. One from that point is actually wave front. So two waves are coming from the two different part of the wave front. So let's say one radiation is coming here and it meet what here. So these two radiation. So now again we want to calculate what, path difference, like we did in YDAC also. Young's double slit also we found the path difference, then we equated with what, condition of maxima and minima. Exactly same thing we're trying to do here. So let's find what is path difference. So one wave is coming this, one wave coming this, right? So what's the path difference? You draw a perpendicular line from here, from this point. This is a perpendicular line, right now. Then This is what your path difference, this one, the Alex, let's call. That's what your path difference. Suppose this angle you call as theta, correct? Na? This is A. Then your path difference, look here, path difference will be simply equal to what? A into what? Sine theta. This is the main thing, correct? Na? What is the extra length of these two waves? One wave is this one wave is this one. It's coming from this end and from that end. From the same wavefront, two waves are coming. Please understand this thing that in YDAC, what happens? Two waves comes and meet from two different coherent sources, right now. But here, two waves come from the same wavefront itself and they meet. I will write this difference at the end. What's the comparison between the YDAC double slit and single slit? So let's see. So this, suppose these are two radiations are meeting at this point, two waves. Then let's call that distance as xn. There's a position of what? Nth bright or dark fringe. This you want to calculate. So path difference is plus what? A sine theta. This much is extra. I draw a normal line from here. So see this triangle. This is a triangle. This side is A. That angle is what? Theta. So that dial axis is simply equal to A sine theta. Correct. Okay, so path difference we have found now A sine theta. Now this will equate with what? Condition of maxima and minima, and we find the position of what? Bright and what? Dark fringes. Okay, let's do this now. Okay, before I write the condition of maxima and minima, I want to show this picture clearly again because the drawing was not good. So once more, let's say it setup of what? Single slit. There is source here. You can see this is source. There is a lens. This lens, one lens. This lens to produce what? Your parallel rays, means a plane wavefront. So these rays are coming from this source, and now we get parallel rays. So we get a plane wavefront. So incident on this opening. This is a wall like, and this is what? A small opening. This much is what your opening, right? So light incident on this, then light comes out from, you have another lens to convert light. So this is your screen here, placed at distance d from here, right? Okay, now what happens? This is central maxima. Two rays coming, there is no path difference between these two waves, right? Now of equal length from point A and point B, they're meeting here, no phase difference, no path difference. So they're making a central maxima. This is what your central maxima. Clear? Now any general point you're talking here. So one wave coming from that end A of this wavefront, right? This wave, see it here, and one is coming from what? This end, that way. So you want to calculate what is the path difference. I draw a normal line from here like this one. So this is what your path difference, this much, AB days in this picture, right? So that's simply equal to what? This side is what? A, and this angle we calling theta. So your path difference del x simply becomes what? A sine theta. If angle is big, we write sine theta. If angle is very small, we write this theta itself. I will talk about this separately, right? Okay, if you understood this, now let's talk about what? When the dark and when the bright fringe will be formed. So we saw the path difference, let's call del x, was A sine theta, where A is what? Your size of the aperture, or slit width, you can say, or slit opening, right? Now you want to get what? Like what your nth, you say like this way, position of nth dark fringe or minima, you want to say. Okay, so what's the condition for here? And the dark fringe, very very important. For dark fringe, path difference should be equal to what? N times of the wavelength, correct na? So this is the path difference we have calculated, and condition for here dark is just opposite to what YDAC. Keep in mind, do not confuse. Young's double slit, like path difference is equal to n lambda, then becomes what? Bright fringe. Here is what? Dark fringe. So do not confuse. Okay, if you equate these two equations, then you get what? You see that A sine theta should be equal to what? N lambda, right? So from here you find the position of what? Nth bright fringe or dark fringe. So you say sine theta should be equal to what? N lambda by A. This is what? The angular position, correct na? Of what? Nth dark fringe, correct na? Where N is equal to what? Obviously like 1, 2, 3, 4. This one. We know that at central always what? Bright fringes formed, then either side of this first dark fringes will be formed. So it's called first dark, then bright first, then dark second, like this way. Okay, so alternate same way like we have done for YDS is formed here, but there is small difference between intensities. I will talk about that separately. So listen here, what's the position of nth bright fringe, nth dark fringe, sorry? So n, name of the fringe, wavelength by what? Size of the opening, or called slit width, is equal to sine theta. This gives angular position. Here you get answer in terms of what? Degrees, right now this formula gives answer in what? Degrees. What will happen? Sometime sometimes the angle will be very small. Okay, if angle is very small, correct na? Then sine theta you can write simply equal to what? Theta itself, correct? Then same equation you will write like sine theta, right? Theta itself is equal to n lambda by what? A. This answer write what in radian, keep in mind, right now. This answer is very important to understand. Let me highlight with this color. This, if you're writing this formula, then answer is what in degrees, like position of like third bright dark fringe at 30 degrees, 60 degrees. In degrees you get answer, right? Here answer will be what in radian, angular position, right now. Here answer will be what in radian. So it's very important to focus on these things. Angular form, degree form, and what radian. Radian will use when the angle is what very small. So sine theta we call equal to what? Tan theta. Now same we want right in what? Linear position also. We want write same answer in terms of what? Linear, like distance we want to find, not angular, because maximum time in exam they ask angular position, like this formulas only we have to use, but they can ask you linear distance also. Like linear distance we have done mainly in what? YDAC. Same we do it here also. Okay, so we're talking linear position. Okay, we want to find what is linear position. How to find? Just you have to put the value of this sine theta only. Okay, an angle is very small, so sine theta again we say equal to what? Okay, let me write here. Sine theta will be equal to what? Tan theta. Keep in mind. Okay, what is tan theta in this picture? Let's go back. So we want to find tan theta. So this is what? Look here in this triangle. This is your maxima. This is your in general. That distance we calling what? Xn, and that distance we calling what? D. So if you make a small triangle here like this way, then this is what your theta, tan theta. So if you see tan theta is obviously equal to what? Xn by what? D. Correct? Yes. So let's replace here. Xn means this is a linear distance of any nth dark fringe by what? Distance of the screen D. So this value you put what in this formula? We put here sine theta is equal to what? N, sorry, n lambda by d. Sine theta we calling tan theta because they are very small angle, so it become xn by what? Sorry, here is what? A. Okay, xn by capital D and lambda by A. So from here you finding now position of the nth dark fringe, that's called xn is equal to n lambda D by what? A. If you can recall, this is exactly similar to what? The position of what? Nth bright fringe in YDAC. If you remember in YDAC, what was the formula? The position of nth bright fringe was n lambda D by what? Small d. Small d was the distance between two slits. Here we have what? A. A is what? The slit width, the opening of the size of that obstacle or opening. Correct? Na? So almost looks similar only, but formula here opposite. This we are talking about dark fringe, and this formula comes in YDAC for what? Bright fringe. Okay, let me write once more if you confuse. We are talking about what? Position of what? Nth dark fringe. So angular position, how you say? Angular position. Maximum time we'll talk about angular position only in case of what? Single slit. Okay. So if you're talking angular position of nth bright fringe, you can say like this way: sine theta is equal to what? You can write in terms of sine theta, that become n lambda by a, right? N lambda by a. Here answer what will be in degrees, correct? Na? Because we're writing sine theta. Or angle is small, then we'll talk like theta is equal to what? N lambda by a. Here answer will be what in radian. Then same answer you can write in terms of what? Linear distance. You can write xn is equal to what? N lambda capital D by small a. This is what your linear means, like meter, centimeter you write here, right? Three ways to write the position of the and your dark fringe. Okay. Yes. Now same we will do for what? Bright fringe. Okay. Let's write position of and bright fringe. Okay. Same way. Look here, general path difference is what you said, del x is equal to what? A sine theta, right? Then del x should be, what should be for bright fringe? 2n plus 1 lambda by 2. This should be the path difference for what? Bright fringe. This is opposite to what your YDAC. So equate them. So when you equate them, you will get this answer. You say that A sine theta is equal to what? 2n plus 1 lambda by 2. So first, sine theta, angular position is what is the answer? 2n plus 1 lambda by 2a. This is the one answer. Okay, this answer again what in degrees, right? No problem, right? Same way you can write now in radian also. If the angle is very small, you can write this theta itself. Okay, let me change color. So this side theta will be equal to, if angle is very small, you write like if angle is small, correct? No? Yes, angle is small, then you write the theta itself is equal to what? 2n plus 1 lambda by what? 2a. Here answer will be what in radian. Now you can write a linear format like that format also. Same thing you have to do. We have to put the sine theta value. Sine theta equal to write tan theta, and tan theta is equal to what, again xn by d. So xn by d. So what answer, xn will be equal to obviously 2n plus 1 lambda, right, capital D by what, 2a. This is what your linear position of what, nth bright fringe, correct? So you wrote what, the position of what, nth, these are the position of what, nth dark fringe, sine theta, theta just in radian, if sine theta then degrees, or linear position here, right now? Okay. So we have wrote what, the position of what, nth bright and dark fringe in case of what, single slit. Now one more thing we want to calculate here is what, your fringe width, like we have done YDAC also. But what is the difference here? In Young's double slit experiment, all your slits has same width. Even the central maxima or any bright and dark fringe, they have equal width. But this is not happening here. Here your central maxima has double width than any other fringe. Okay, let's talk about this. So we write here heading, let's call fringe width. So what important point you have to remember here first, that central maxima has double width than any other what maximas. So it's very important here. Central maxima has double width than any other maxima. But if you remember that in case of YDAC, all even central maxima and any other maxima has what, same width only, but not here. So here we write two cases. If they are asking width of central maxima, what is width of central maxima, or we can write any other maxima, okay, any other fringe or maxima, okay, any other fringe, or you say maxima, right, doesn't matter, any other fringe, what should be width, this has what, double width. So how we write fringe width formula first, just similar to what like we have done YDAC only, okay. So if you remember like a YDAC, what was the fringe width? We wrote beta symbol, that was, if you remember, lambda d by d, right? Exactly same formula here also. Here fringe width beta will be equal to lambda d by a. There we call the distance between two slit. Here we have slit width only, right? Now a. This is what fringe width, linear fringe width. If you want to write angular fringe width, right? Angular. Then what you do? You bring your, you write like theta is equal to what, beta by d, right, or simply lambda by a. This is called what, your angular fringe width. This answer will what, in radian, keep in mind, okay. When you write just theta alone, remember that always in radian SI system, okay. Now central maxima has what, double width. So width of central maxima will be 2 times of any other fringe, 2d by a. Look here I wrote just lambda d by a, here I wrote double. Same way angular width you want, right, of central maxima, same answer, theta will be equal to what again, like beta by what, d, or you say 2 lambda by a. So 2 lambda by is answer. Here what, just lambda by a answer, right? Yes. So this is important. You have to remember this. Okay. So these are three things only you have to do here in case of our single slit: position of nth dark and bright fringe, and the fringe width. Fringe width, again there is a difference. Central maxima has double width than any other maxima. Okay. Okay, now we'll do a simple comparison between what, your interference and diffraction. Then we'll do numerical problems on what, diffraction. Okay. Okay, so there is a simple comparison between these two, interference and what, your Fraunhofer diffraction. Look here. First, how interference happens? Interference happens by superposition of two waves. Okay, by superposition of two waves coming from two different coherent source. Here we need like two coherent source, two waves comes and they interfere. Then what? Your patterns are formed, dark and bright fringes. But what happens in like diffraction? Here, what happens? Two waves come from what, same wavefront only. Like it's a superposition of what, two waves coming from two different part of same wavefront. Here we need two waves from two different coherent source, keep in mind, but here we need two waves from the same wavefront only, right? Okay. Interference, what happens? All bright lines are equally bright and equally spaced. Their width is exactly same and brightness also same. Means intensity is what, same. But here intensity is what, not equal. And also what, correct na? Brightness not equally bright, and they are not also equally wide. Correct na? Brightness or intensity will decrease on either side, right? Okay, here dark fringes are all are dark. Means there's contrast between the bright and dark is very clear, very good contrast here. But in this case, your diffraction, the contrast between bright and dark fringe is not good. Your dark, okay, lines are perfectly dark. The contrast is what decreasing, right now. The contrast will not remain same. Okay, interference we get large number of fringes. Large number of fringes are formed here, but here very few fringes only formed in case of what diffraction. Okay, we understand this intensity concept by drawing the picture actually. So let me draw and understand you the intensity concept. So what happens in case of interference? Okay, in case of interference, what happens? The intensity of all bright is equal and all dark also equal. So interference. Suppose I draw like say this side, this is what your intensity side, okay, and this is what your central maxima. Suppose this is the intensity I naught of central maxima, then intensity of next bright will be also equal actually. All bright fringes will have equal brightness and all dark also has what equal darkness, right now. So like this is called your central maxima, cm, correct. Then this is like all you call first bright, this is called second bright. On the other side also first bright, this is second bright. Then you know dark fringes, dark will be like equally dark. This is your first dark, this much will be your first dark, right. That's this is what your second dark. This side also is a first dark, then this is called what your second dark. Correct. So they have equal intensity. Like all bright has equal intensity. I naught only, right now. Every fringe has what equal intensity and width also equal. Suppose the center maximum width is equaling lambda d by d here, right now. Then any other fringe like this also have same width only lambda d by d. Any fringe you talk, they should have exactly same width. This is what happening in interference. But what happens in diffraction? This is not happening. Diffraction, the intensity and width are different. Suppose I draw same curve, intensity versus distance. Look here how it looks. Suppose this is what your central maxima. It has maximum what intensity. Okay, this is what your central maxima. Central maxima intensity. Let's call it I naught. So width of central maxima is what 2 times of lambda d by a. Correct. This is width. Now next bright. Suppose this is your next bright. Intensity will be reduced. Again, next bright intensity is what even reduced. Both side this is happening, right? Like this. Actually, if what happens, suppose this is central maxima, is intensity I naught, then this is your first maxima, this is your second maxima, this is first maxima, this second maxima, right? So intensity of next maxima will be reduced by actually by 22 times. Intensity of this will be what? I naught by 22, and next your bright will be around like I naught by 61 times is reduced. So intensity is what sharply reducing on what either side of your central maxima. But you see in interference, the intensity remains what I naught, doesn't change. And width also same. Here width of central maxima is what 2 lambda d by a. Any other maxima you talk like this maxima, it becomes just lambda d by a alone. Right. Central maxima has what double than what any other fringe. Correct. And intensity also reducing both sides. This maxima also has like I naught by 22, that has what I naught by 61. So intensity reducing in what either side, correct. So this is a main difference between what interference and diffraction. Okay, after this now what we'll do some numerical problem based on what diffraction. Okay, okay, let's start. First problem is this: light of wavelength 6000 angstrom is incident normally on a slit of width. Slit width is given. This means 10 power minus 5 centimeter. Find out the angular position of second minima from the central maxima. So they are asking angular position of the central, second minima, dark fringe. So you know how we write? We write like sine theta is equal to what? N lambda by A. This is called what your angular position of what? Nth dark fringe or what minima. Okay, let's put N is given what second? Yes, given second minima they're talking. Wavelength given 6000 angstrom. So 6 into 10 power minus 7 is 6000 angstrom is given right now. So 30 that angstrom is 10 power minus 10. So 30 I remove. So I'm writing 6 into 10 power minus 7 by the width of the slit, which is given 24 into 10 power minus 5. So 24 into 10 power minus 5, minus 7. Minus 5 centimeter given, 10 power minus 5 centimeter. I'm writing as 10 power minus, centimeter. I'm writing as what? Meter. Okay. So this power get cancelled. Okay, this is 12, this is what 24, this becomes what 1 by 2. So we're getting as like sine theta is equal to 1 by 2. So theta comes what 30 degree. So this is the angular position of the second minima, second dark fringe when this much wavelength is given and this the slit width given, right? Okay, let's move to the second problem. Second problem is saying that light of wavelength 6000 angstrom is incident normally on a slit of width. Again, A given, wavelength given. Calculate the angular width of the central maxima on a screen at distance of what 9 meter. D is given. So they're asking width of the angular width. What width? They're asking angular width of the central maxima. Okay, first, what is normal width formula? Like linear width of central maxima is 2 lambda d by a. Then angular theta we write quite simply like what? 2 lambda by what a. This is what angular width. 2 given, lambda is given 6 into 10 power minus 7. Again, 6000 angstrom was given by a. Slit width is given 0.2 mm. So 0.2 mm. Correct? Mm is 10 power minus 3 and 0.2. So you can write 2 into 10 power minus 4. This 2 you can cancel. So 6 into 10 power minus 3 meter, or you can also call as 6, sorry, not meter, I am writing here because finding angle. So this answer is what in radian. Yes. What is the answer? Radian. This much is 6 into 10 power minus 3 radian. When angle is very small, we write like this format. So answer is what in radian, not degrees. Degrees like we have done previous sine theta. Okay. Okay, let's move on to next problem. Question number 3. They said light of wavelength 5000 angstrom is incident on a slit of width given A given. Find out the width of central bright screen on place a distance of 2 meter. So here they are asking what normal width. They are asking linear width. Like previous question, they have asked what angular width. So what we will do? Beta is equal to what 2 lambda d by a. This complete formula I will write, right? Suppose there any other fringe width they ask, then it's just lambda d by a. Your central maxima has double. Okay, so 2 times lambda means 5 into 10 power minus 7. D means what 2 meter by a means 0.1 mm given. So you can write 1 into 10 power minus 4. So you see this become 4, this become 20. 20 into 10 power minus 3, or say 2 into 10 power minus 2. Again, sorry, this is answer what in meter, or you can say like 20 mm, also you can say millimeter, because this is nothing but 20 mm itself. Here they are asking linear width, and the previous question we have done here they are asking angular, so I wrote angular formula, right? Okay, so let's move to the next problem. Question number 4, and in this question they're saying that light of wavelength 6000 angstrom is incident on a slit of width given, means A given, screen is placed 2 meter away, so capital D is given. Find the position of first dark fringe and width of the central maxima. So they are asking position of the first dark fringe. Correct. Okay, so we know that sine theta is equal to n lambda d by a. So I don't know, like you have to see your options whether answer is given in angular format, like angle is given, or given distance given, right now both format they can ask you. I think they asking because d is given, they asking in what? If they asking angular, this is the answer, right? Sorry, I wrote a little wrong here. Not linear, xn, linear distance. So let me write it clear. Xn is equal to what? N lambda d by a, right? This is the linear distance of what? Any dark fringe. So what is the answer? Xn will be equal to n. They are asking first dark, so n is what? 1. Wavelength given 6 into 10 power minus 7. D is given 2 meter, and width is given 0.3 mm. You can write 3 into 10 power minus 4. This goes 2 times, so you're getting 4 into 10 power minus 3 meter, or you can say 4 mm. This is the distance of the first dark field. This is a linear distance. By chance they ask angular, then angular formula like sine theta is equal to lambda d by what a. Correct. This will the angular position of that fringe. Okay, here one more question they're asking, what's the width of the central maxima? Okay, beta they're asking, which is what 2 times of lambda d by a. This is the width of the your central bright fringe. So 2 times lambda is given 6 into 10 power minus 7. Width is, distance is given 2 meter, and a is given 3 into 10 power minus 4. Okay, this goes 2 times, so this becomes what? 4 8 8 into 10 power minus 3 mm. Correct. This is the width of the any central maxima. Okay, yes. Let's move to next question. So in this question, it's a special question. So before I solve this question, let me give some idea that how to solve this question. Okay. So what happens? Let's write a special case in YDAC, sorry, in single slit, special case. What happens now? If screen is placed, the screen that you're putting, the distance D is placed at focal point of second lens. Remember that picture? This was the source. This was one lens. This used to make a plane wavefront. There was opening here. Then another lens was there, and this was the screen, if you remember, right? So this is second lens L2. This is lens one. Suppose this D. This means this screen is placed at the focal point. Means right, the waves comes that meet it here, right? So D is simply equal to the focal length of this lens. If what happens if screen is placed at the focal point of second lens, then what happening? The distance D is simply equal to focal length of the second lens. Yes or no? Yes. So all the formula that you wrote, you can write those formula in terms of focal length of this lens. This lens focal length you can write instead of the screen distance. They say that the screen is placed at the focal point of lens of having focal length, suppose something like 10 centimeter, right now. So this distance D screen is simply equal to the focal length of this lens. Correct. So how the formula will get modified? Look, for example, suppose I say you want to find your minima or your dark fringe position. Then how you wrote? You wrote like sine theta is equal to what? You wrote like n lambda by a, right? This was angular, no change. But linear, how you wrote? Linear log xn is equal to what? N lambda d by a. This was the formula. So instead of d not given, then what is given? Focal length of the lens will be given, and the screen will be placed at the focal point of the second lens. Then same formula you can write like this way: n lambda f by a. Very very important, right? So the screen distance simply equal to the focal length of the second lens, right? Like this, a position of what? Linear position of what? Your end minima. Same you can write for your maxima also. Suppose you want to write fringe width. Then how you write fringe width? Fringe beta you wrote, beta was n lambda d by a. This is the fringe width. So suppose focal length given, then it becomes n lambda f by what? A. This is okay. Suppose it's a, oh sorry, okay. Suppose like this is a normal I wrote. This is central maxima, then this becomes 2. Here also becomes what? 2. Sorry, you have to remove n. I'm writing little wrong. I write this side. Fringe width. Central maxima, I'm talking what is the fringe width of central maxima? Then you write beta is equal to 2 times of lambda d by a. So I'm saying instead of d, if focal length is given, you can also write 2 lambda f by a. This also you can write. Any other fringe, right now? Any other maxima, then write beta is equal to what? Lambda d by a. So you can also write lambda f by a if instead of your distance of screen they have given focal length of this lens. So same answer only, just instead of d we putting the focal length of this lens because screen is placed at the focus of this lens, right now? Okay, so now do that questions. This question was like this. They said in front of a diffraction, the pattern of single slit is formed at the focal plane of a lens of focal length 1 meter. Means your f or d is given, right now. The width of slit is given, again a given. If third minima is formed at distance of 5 mm from the central maxima, calculate the wavelength. So here distance of third minima given. Let's write the distance of nth minima is given by this formula n lambda d by a. So here d is not given, so you can write n lambda f by a, right now, because instead of d the focal length is given. Okay, we have to calculate, all values are given, we have to calculate the wavelength. So rearrange this formula: xn into a by n into what? F. That's what your wavelength. So what is the answer? Distance is given 5 mm. 5 into 10 power minus 3. A is given 0.3 mm. So you can write 3 into 10 power minus 4 divided by n. And the size third minima, so it's become 3. And focal length is given what? 1 meter. So this get cancelled here. We're getting 5 into 10 power minus 7 meter. Or wavelength you can also write as what? 5000 angstrom. 5 into 10 power minus 7 meter you can write as 5000 angstrom, right? Okay, so do not confuse. If the focal length is given instead of the screen distance, the d is equal to what? Simply f. In all formulas you can do this. Okay, so this all about what? Diffractions. So now you should solve the problem from your exercise 1, and if you have any doubt, please put in the comment. I will help you. Thank you so much and have a good day. Bye.